我刚看过那个你们期中考平均好像超高，对啊，但是那个上机考平均好像蛮低的。这个应该你们等于说代表说你们的演算法的知识跟你们会写程式的能力不成正比哦。这个可能要加强一下啦。这个 OK， 我希望你们这个至少你们会的东西能够把它写成程式弄出来哦，要不然这个实在是看起来实在是not presentable。OK， 好，那 OK， 所以 I ask you one question like at the end of our last lecture. So what do you think? 你们觉得 binary search tree sort 跟这个 quick sort， 你们觉得哪一个比较好？或者说给你很大量的那个数字就是那个 number 的话，很大量的 record， 你们会用哪一个？Which sorting algorithm are you going to use? 有人有答案吗？没有，都没有。OK。如果说 if we do not consider anything else, okay, probably quicksort is still a better choice. Okay, why do I say that? Okay, because even though the time complexity wise or like in practice, both sorting algorithms are fast enough. Okay, but quicksort is the in-place sorting. Okay, in-place sorting. It doesn't require extra storage space. OK， 你知道 quicksort 你就直接在那个 array 上面去做嘛，对不对？对，所有的事情可以被 everything can be done. OK, without additional storage space. OK, but the binary tree, OK, binary search tree sort, obviously you need like a linear amount of storage. OK, because you need to build that binary search tree, right? So that requires some additional storage. Okay, I'm not saying like it is like that bad because after all the storage is considered much cheaper nowadays. OK， 就是现在那个 memory 也变便宜嘛，那个这个硬碟也变便宜。OK，so it may be a good idea. OK, if you can speed up the speed. I mean with if you are willing to give up some storage space, but in terms of speed, like quicksort is not any slower than binary search tree anyway. OK， 就是实际上来讲的话 ，binary search tree 不会比 quicksort 更快，就是它们事实上是差不多同个 level。那在同个 level 下面，如果可以省更多的那个 storage space， 当然 quicksort is still considered a better sorting algorithm. OK, yeah. So just want you guys to understand there are different considerations. OK, like the speed of the sorting is one consideration only. OK, there are other considerations you need to you need to think about. OK, so then, as I said, we are done for the day, for this chapter, and then we will be continued on the topic of the search tree. Okay, binary search tree is just one of them. Okay, but there are multiple such trees out there, and many of them are, have like a very good properties. For example, okay, a lot of trees are balanced. Okay, what do we mean by balanced? Okay, a tree is said to be balanced. Okay, it means like the height is guaranteed. Okay, the height is guaranteed. It's not like okay, you have average case. No. It's like worst case is still guaranteed to be log n. Okay, the height will be log n. Okay, so obviously, like if the height is guaranteed to be this to be bounded by big O log n, it is very, very good, right? It is very, very good because a lot of things has something to do with the height. For example, the insertion. For example, like or like search. A lot of things, or like to build a tree. Okay, it has something to do with the height. Okay, that we have just seen that like in our discussion of the binary search tree. Okay, so as I said, there are many such data structure out there. Okay, such as AVL tree, such as 2-3 tree, 2-3-4 tree, B trees, and the red-black trees. Okay, so in data structure, what did you learn? You should have learned AVL tree in your data structure class. Yes or no? 你们学了什么？你们资料结构学了什么？就是这种 balanced search tree. Okay, theoretically speaking, in your data structure class, you should have at least learned AVL tree and the B tree. Supposedly, is it? 是吗？没有。诶，那你们数学的什么东西？就学数。啊？什么 tree？Selection tree。奇怪了 ，AVL 跟 B tree 应该是一定要学的啦，在资料结构里面。OK， 如果不学，了不起不学 B tree 啦 ，AVL 至少是一定要学的。OK， 那你们的 data， 你们是哪一个老师教 data structure？ 张老师是不是？咦，奇怪了，还是他其实 hidden agenda 是希望你们留在中央之类的？没有啦，开玩笑啦，开玩笑。对，那个，因为讲老实话啦 ，AVL tree 基本上在那个考研究所这样一定会考的、啊。对啊，这不教有点那个，我觉得，但是当然我也不是你们资料结构老师，我没办法那个强迫老师去教什么东西啦。我只是跟你们讲说，好，那你们如果说你们至少你们自己要知道，有一些东西自己要 pick up， 像这个 AVL tree 你们自己要去 pick up， 好不好？因为我很显然we are going to cover red black tree, okay, in this chapter, but we don't have time to cover all the other trees, okay? AVL trees 基本上资料结构会考，那 B tree 就看有一些学校有教，有些学校没有教。那 B tree 很重要，就是因为它在做 indexing 的时候，在那个至少你说你在学资料库的时候，它至少也应该也会教了。那但是我们系上，因为我们资料库不是每年都开哦，我们资料库基本上是蔡孟峰老师开，然后我记得他是每2年开一次。你们如果多对那个资料，其实你们应该要去学资料库的。我觉得资料库是一个很好的课哦。Database is a very good class. I mean, just like networking. Okay, network is like considered like a service now. It's like you use the network like a concept in many different different research. Okay, you need to know like some basic networking concept. I mean, similarly, in many research field, okay, you need to understand like some database concept, okay, in order to do well, okay， 因为太多地方用到资料库了，所以我是建议你们有机会，虽然在我们的系上，我们很特别的，我们把网络的课变成必修，可是 database 不是必修，但是这个其实应该这样讲，这两门课应该以现在来讲，应该是差不多的重要程度啦。所以我的想法是觉得说，既然它现在不是必修课，但是你们如果它有开的话，我建议你们去修 ，OK， 就是它2年开一次嘛 ，OK， 所以 anyway， 所以如果说 B tree 至少资料库会教啦 ，at least database will teach this，OK，and avial tree, I mean if you don't get it from like a database, from the data structure course, I mean you should try to learn it by yourself. 2-3 tree, 2-3-4 trees are kind of like a variation of AVL. So once you learn AVL, I think like this variation should be easy to learn. Okay, at least 2-3 tree. So for red-black tree, okay, we are going to talk about this. Okay, it is kind of very different from the previous ones. Okay, so obviously we don't have enough time to finish this chapter. Okay, so I hope to finish. So remember I just told you I will assign like homework assignments to you like today, right? So my homework assignment will cover hashing and binary search tree, but not red-black tree. Red-black tree will be covered. I mean, the homework for red-black tree will be given out like next time. Okay. So what is red-black tree? Okay, obviously it's a tree, okay? But this data structure requires extra 1-bit color field in each node. So each node has 1 additional bit to indicate its color. So a node is either red or black. So we have 4 important red-black tree properties. Very, very important properties. First, every node is either red or black, which is indicated by that additional bit. Okay? And second, the root and the leaf nodes are black. Okay, it is guaranteed that root and the leaf nodes are black. Okay? And the third one, if a node is red, its parent has to be black. OK， 就是红色的点，它的父节点一定是黑的。OK，the reverse is not necessarily true. OK，a black node, its parent is not necessarily red. OK， 就是红色点它的父节点一定是黑的。但是黑色点父节点不一定是红的 ，OK， 不一定是红的 ，OK。And remember, this is the search tree, OK. So all symbol path from any node X to a distant leaf node, OK. 从 root 节点到任何一个 leaf node 的这个 symbol path have the same number of black nodes. We indicate that number of black nodes as black height. Okay, black height. Okay. So we have these 4 properties. Okay, then now let's give you an example of red-black tree. And you can see I emphasize that this is a search tree, right? So you can see that if you try to traverse this tree in order fashion, you get the sorted numbers, right? The numbers are sorted. So a red-black tree must be well, a search tree, okay, or it's a binary search tree, okay, to be more specific because it's a binary tree, okay, and you can see that each node is associated with a color, and you can see, okay, first, every node is either red or black, and the leaf node also has, I mean, we just put an NIL here to indicate it's a leaf node, but actually they are nodes too. But it's just like a leaf node do not have number. But it also have, the leaf nodes also have color. Remember, second one, the root and the leaves are black. So we do not draw the leaf node, but they are black too. Okay, so you can see that the root is black. Leaf nodes are also black. We don't have a node for leaf node here, but the leaf node, you can imagine, I mean, conceptually, these leaf nodes are black too. Okay? And if a node is red, then its parent is black. For example, this red node, its parent is black. This red node, the parent is black, and so on. Okay, but you can see that the inverse, the vice, is not necessarily true. Reverse is not necessarily true. The black node, its parent could be black. This black node, its parent is black. The leaf node, its parent is black too, right? So the red node, the parent has to be black. Okay, that's the only requirement. Okay? The last one. All simple paths from any node x, okay, to a distant leaf have the same number of black nodes. So from the root, okay, to its for example to the other to all the leaf nodes, you can see the black height is 2. It will traverse through 2 black nodes. Okay. And for this one, the black node height is 2 as well. Okay? And this one, the black node height is 1. Okay? Here, okay, let me make it clear. Okay? When we say the black height, okay, it does not include its own color. So that's why, okay, for example, from here, okay, because this leaf node like is black, so black height is 1, black. But here, okay, from here to the leaf node, okay, we only count this black node, so the black height is 1. Okay, we do not add this node's color into the depth, into the height, the black height. Okay, so that's why this one is black height is 2. Otherwise, you will see like, oh, the black height, including the root, it should be 3. No, it's just 2. Okay? So far so good, right? Okay, so this example should be very easy to understand. Okay, once you know, so this is a red-black tree. This is red-black tree. Okay, and then how about a red-black tree with n keys has height, okay, h small or equal to 2 times log n plus 1. H is the height of the tree, okay, and n is the number of keys. Remember here, okay, the key only appear in the internal nodes. Okay, the key only appear in the internal nodes. The leaf nodes do not have key. The leaf nodes do not have key. Okay, so we have this theorem. And the book prove this by induction. I hope you can check it out. Okay, but here I'm going to provide you a different proof. Okay, a different proof. Okay. Let's try to merge the red nodes into their black parent. Because we know each red node has a black parent, right? Each red node has a black parent. So, for example, this node can be merged in here. This node can be merged into here, and so on. So what happens become like this, right? Of course, after you merge, after this merge, each node may have more than one child, more than two child, right? More than two children. Each node may have more than two children. For example, this one, the root has 3 children, and this node has 4 children, okay, and so on, okay. So once you do that, this process is going to produce a tree in which each node has either 2, 3, or 4 children, right? Right? Either 2 or 3 or 4 children, as I have indicated here, right? Okay. And this is similar to 2, 3, 4 tree, okay? Has uniform depths. This tree, we say this tree, the height is h prime, okay? Of course, this height may be different from h, because you can see previously, this height, what is the height? 1, 2, 3, 4. I think it's a 4 or 5, I mean, right? But now, I mean, after the merge, the height is different, right? So this h prime, okay, is different from original h. Okay, I just want you to be aware of that. Okay, so then, okay, let's think about this. First, we know h prime must be greater or equal to h divided by 2. Why? Because at most, half of the leaf nodes on any path are red, right? So, I mean, you are doing the merge, right? You are doing the merge. At most, only half of them on the path are red, right? So this compression, you can say this is kind of like a compression. This compression wouldn't be able to compress more than double, right? For example, like in this path, it has a black, red, black, red, black, right? So you can, I mean, this compression is going to eliminate 2 red, right? That's it, right? That's it. Okay, it is still smaller than 5 divided by 2, right? Okay, so basically, okay, so h prime, the resulting height must be greater or equal to h divided by 2, right? Okay, so we have that. Okay, and the number of leaf nodes in each tree is n plus 1. We know that. Okay, what is n? Remember, n is number of keys, right? The number of keys. Okay, or put it another way, n represent number of internal nodes. For a binary tree, we know like a number of internal nodes is 1 plus the leaf nodes, right? 1 plus the number of leaf nodes. I mean, well, you can check it out. For this example, we have how many keys do we have? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 keys, right? We have 8 keys. 1, 2, 3, 4, 5, 6, 7, 8. How many leaf nodes do we have? 1, 2, 3, 4, 5, 6, 7, 8. Oh, then we have an additional one. Additional one here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So number of leaves node will be 1 plus number of internal nodes. Because in the red-black tree, the keys only appear in the internal nodes. So we have like one leaf nodes in each tree is n plus 1. And n plus 1 must be greater or equal to 2 to the power of h prime, right? Because like, you know, here, I mean, if you each node has 2 leaves, then it's the 2 to the power of h prime, right? But here, I mean, because each node may have 2 or 3 or 4 leaf nodes, right? So this n plus 1 must be greater or equal to 2 to the power of h prime, right? Okay, and with that, you do a log. Okay, you try to do a log. I mean, apply log on both sides. So this log n plus 1 is greater or equal to, because both are, obviously positive number greater than 1. So this inequality still holds. Greater or equal to h prime. Okay, h prime is h divided by 2, right? Well, greater or equal to h divided by 2. So we have h small equal to 2 times log n plus 1. Right? So we have this. A red-black tree with n key has height, this one. Okay? So this is important because, remember, we want to discuss the balanced search tree. So the tree has to be bounded by log n, right? So this is like we guarantee this, the height is bounded by log n. You can see that. Okay? So it's the query. Okay, we can directly, obtain from this theorem. The query, search, min, max, successor, and the predecessors all run in big O log n time on a red-black tree with n nodes. Why? Because, well, it's obvious. Because the height is bounded by log n, right? So all these operations, okay, search, min, max, successor, predecessor, I mean, they have something to do with the height, right? Height of the tree. Okay, the worst case, I mean, so yeah, basically they are, their type complexity is big O log n. Okay, so I think yeah. So we are, okay. As for modification, I think we will stop here today, okay? Because the next one is about insertion and deletion, okay? The insert delete are more complicated. It involve a couple of modifications. Not only we need to obviously do the insert or deletion, okay, operation itself. Also we need to consider a color change and the restructuring, okay, in other words, rotation. So all this. So I think we'll cover these things next time, okay? So I guess that's it. Any question? Yeah, if no question, remember I will give out the homework assignment tonight, okay? So please, remember to check it out. And yeah, that's about it.